get the recording started. And let's start talking rotations and the moment of inertia and stuff like that. So, first thing you want to know is, what exactly is a moment of inertia?
That's the stuff that keeps it moving, right?
The stuff that keeps it moving. That'll definitely get you full marks. Give me more info, more details. Is it what
Like
keeps something moving, or go ahead?
I think it's or it describes an object that's already in motion.
In what way?
Um,
What kind of
it's like
motion?
rotational motion.
Mm-hmm. So, how do we calculate the moment of inertia?
The moment of inertia is usually set around a point. So it would be like the mass.
So, what sort of point?
The center of mass, or an axis.
Some sort of an axis? Is that like the axis is rotating around?
Yes, the axis that it's rotating around.
So, how do we actually calculate the moment of inertia?
It depends on what we're calculating it for. I think that for a regular rod, it was 1/12 mass times the radius squared.
Not the radius, but
Well, the length.
the length.
The length, yeah.
What if it's just a bunch of point charges? Oh, sorry, not point charges. I'm thinking 122. What if it's just a bunch of point masses? Like if this is our axis of rotation, or if this is our axis of rotation, and we're going to be like rotating around like this, for example, and we have a bunch of little point masses like this. How do we calculate the moment of inertia for all these?
We would find the total mass of the points.
The total mass for all the points added together?
Yes, and take a weighted average of their location and, or I guess the center of mass of the points.
And then what?
And then multiply it by the length that they're spread across.
Not quite. I think it's more, we have to think about the distance each mass has from the axis of rotation. There's an equation on the formula sheet that you can use.
Oh, it would be the total inertia.
The
Wait. Oh, the inertia equals the average of the masses times the radiuses. I guess their distance from the axis.
It's not the average, it's the sum
Oh, the
of,
sum. I'm
so
sorry.
it's the sum of each mass times its distance from the axis of rotation squared. So it's essentially the moment of inertia I is equal to the sum of each individual mass, m sub I, and then the radius each mass has, for example, this radius boom, 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 etc. Each distance r sub I squared. And this is the case for any set of point masses, or even not even just point masses, but we could technically use this to find the moment of inertia for like a rod or a sphere or a solid disk. How would we do that? I mean, if we have, for example, let's say we have a sphere and it's going to be rotating through its center. How many point masses are there in a sphere?
So the mass is spread across the whole sphere?
So would that be like essentially an infinite number of point masses?
Yes.
But each mass is infinitely small, right?
Yeah.
So there's a way we could actually integrate over the entire volume of the sphere to find the moment of inertia. We don't actually worry about that in this class, and we just memorize the actual final values. But if you take any higher level physics classes or engineering classes, you'll start to see some of these derivations. And it's sort of fun, but it's not too complicated. But we don't cover it in this class. So essentially, a moment of inertia is a way of defining how much resistance, I'm putting that in quotation marks, something has to rotating. Essentially, the same way mass, the mass of an object, is effectively a way of resisting motion. Obviously, if something is more massive, it is harder to accelerate it. It's sort of the same way with a moment of inertia, where if something has a high moment of inertia, it is harder to rotate it than something that has a lower moment of inertia. And the moment of inertia then has to do with the actual rotation of an object and, like, for example, the rotational energy, or how much energy it takes to make it rotate. So what is a torque? The other main thing we want to understand.
A force applied to make something move, right? But it's applied so that it moves in a rotational sense.
Mm-hmm. And how do we calculate the torque?
Torque would be the force times the distance?
Sort of. You're sort of scratching the surface, not times the distance.
I remember that there are two vectors, so the force vector and the
the force vector and the displacement vector, or like the distance from a set point that we're calculating the torque at. So what is, you said something about multiplying them, or like it's force times distance. What's the vector equivalent of a multiplication? It's on the formula sheet.
Oh,
we can't exactly just multiply two vectors together.
Oh yeah, the we added the different components of vectors, so the x component and the y component. I mean the x component of the vectors and then the y components of the vectors.
So we're adding them together? We have to take the cross product of the force and the distance. And specifically, it's actually the other way around. The torque is torque, which is this little tau, is equal to the displacement vector. So essentially, like if we have a rod coming out from a wall, for example, if we have a force acting on it like this here would be r, the distance out from the wall, and then this would be the force. It'd be the displacement vector crossed with the force vector. What exactly is a cross product?
Oh, the cross products. I'm not sure.
So a cross product is effectively a way of multiplying vectors together, where first of all we want to find the magnitude of a cross product. The magnitude of the cross product is just it's the magnitude of each of the two vectors. Essentially, it's just r times f times the sine of the angle between them. What would be the sine of 90 degrees if, for example, r goes out like this and our force is acting straight downwards on a rod hanging out from a wall?
That would just be 1.
Exactly. Sine of 90 is 1. And what if our force is acting opposite to our displacement vector?
Then it would be 0.
Exactly. So essentially, the way we find the magnitude of our torque is it's r times f times the sine of the angle between them. So essentially, if r and f are perpendicular, they're going to be a maximum, and if they're parallel or anti-parallel, there is no torque. And now for the direction of the torque. Do you know how we find the direction of a torque? You know how we find the direction using... Have you heard about right-hand rules?
Oh, yes.
What is a right-hand rule? Or how do we use the right-hand rule to find the direction of the torque?
So the torque would be the direction which our thumb points, but then we would have to align our fingers with the rotation.
Yep. So let's say we have our r vector is out to the right and our force is directly downward. How do we find the direction of the torque here?
I'm sorry, which one's which?
R is to the right and our force is downward.
So we would...
What direction is the rotation going to be in? Clockwise or counterclockwise?
Clockwise?
Yeah, exactly. If we pull down on the rod, it's going to want to rotate clockwise. So what direction would our torque be in?
It would be inwards.
Exactly, into the page. We rotate our fingers around in the direction of the rotation, and so our torque points into the page. Now, when I say like the torque points into the page, I don't really like to think about it like that, because the torque is this rotation here. This rotation is the torque. It's just that, like, the way we define it, the direction of the torque is always perpendicular to the other two, and it just represents this rotation which goes around the torque. It's a bit confusing, and there's a reason why physics doesn't really make much conceptual sense, but essentially all you need to know is R cross F is going to cause a rotation. The rotation is pretty simple to understand. If we pull down, it's going to want to rotate clockwise. If we were pulling up, it would want to rotate counterclockwise. And if we want to find the magnitude, it's R times F times the sine of the angle between them. So those are the two main things you need to understand for solving most of the problems you'll see over the next few classes. You need to understand the moment of inertia, and you need to understand what a torque is, and you need to be able to relate the torque to Newton's laws of motion for rotational motion. What's the equivalent of, so for example, what's Newton's second law?
Newton's, an object at motion will remain at motion unless something opposes it.
That's the first law.
First law.
What's the second law?
Force times mass. Mass times acceleration is the second law?
Yeah, exactly. Force is mass times acceleration. So, what is the rotational equivalent of F equals ma?
Would be so alpha times would it just be the last one? The last equation on the sheet?
Yeah. So we have the torque, which is, we're talking our net torque here, obviously if we have multiple torques acting on something. Our net torque, because torque is essentially a rotational force, is equal to our moment of inertia, which is essentially our equivalent of a rotational mass. It's how much something resists rotation, times the angular acceleration, the rotational equivalent of acceleration. And so we like to sort of describe that as Newton's second law for rotation. And that's one of the main things you need to understand here is you can calculate a torque on an object and be able to apply Newton's second law of rotation to understand how much it's going to accelerate, or how much its rotation is going to accelerate. So this material is a bit wonky, and I think the main thing, I feel like you're being a bit overwhelmed by the concepts, but you came into the session, you mentioned you were really confident with the material, and you were really comfortable with it for actual problems, right?
Yeah, for calculations, I feel like I'm a bit more comfortable.
So let's just hop into some examples and just make sure that confidence, I need to make sure that confidence is actually warranted. Dun dun dun. So we're going to go ahead and have a solid quarter kilogram disc, radius of 5 centimeters, is going to be starting at rest at the top of a 30-degree inclined slope. And we're going to go ahead and let it roll down the slope without slipping. Essentially, it's just going to roll, and we don't have to worry about any friction with the disc. It's not going to be slipping. So the first thing we want to know is, how do we find the moment of inertia of the disc?
Moment of inertia of the disk would be 1/2 times its mass times its radius squared.
Yep, exactly. Half mr squared. And we could go over the derivation for that, but again, we don't need to worry about that for this class. We're given all the moments of inertia that we'll need for this class. Half mr squared. So how would we find the velocity of the disk after it's traveled 2 meters? And what about the angular velocity?
The regular velocity and then the angular velocity.
Mm-hmm.
To find the regular velocity, well, we know the distance that it travels.
Mm-hmm. It travels 2 meters, and we know the angle of the slope. How would we actually approach this problem? Let's say, first of all, what is the... How do we quantify the rotational kinetic energy of an object?
Oh, that would be 1/2 of its inertia times the angular velocity squared.
Exactly. Half I omega squared. So K... We'll actually use the total kinetic energy of an object is half mv squared plus half I omega squared. Once again, it's pretty much the same thing as half mv squared, where the moment of inertia is the rotational equivalent of the mass, and omega is the rotational equivalent of the velocity. Now, how do we relate the velocity for something that's rolling without slipping to its angular velocity? How do we relate velocity and angular velocity?
Well, even if angular velocity is constant, the regular velocity might not be. Oh, it's what was um, um do we relate them using the centripetal acceleration?
How would we do that?
Well, the centripetal acceleration is equal to the angular velocity squared times r, but it's also equal to the regular velocity squared over r.
So the angular acceleration is v squared over r? Is that what you're saying?
Yes.
So alpha is equal to v squared over r? So then how do we relate alpha to omega? Give you a hint, there's an easier way to approach this, and it's actually given on the formula sheet once again.
I see. Um, the velocity is equal to the radius times the angular acceleration.
Exactly. Not the angular acceleration.
Oh, my bad. The angular velocity.
Exactly. So essentially, we can relate all our different quantities by just simply multiplying the angular version times the radius to get the actual velocity. So, for example, the velocity is equal to the radius times the angular velocity. And it's the same thing for acceleration. The acceleration of the disk rolling down the slope is going to be the radius times the angular acceleration. And the total distance that the total distance that the disk rolls is equal to the total radians that the disk rotates times the radius itself. So our velocity is equal to the radius times the angular velocity. And what was the moment of inertia of our disk again?
Oh, 1/2 mass times radius squared.
I is equal to half m. I'm actually going to keep it consistent and write little m r squared. Using these two equations, we can go ahead and write our kinetic energy in terms of just one set. Instead of it being in terms of m, v, I, and omega, we can just write it in terms of just mv or just I omega. How would we do that?
I guess we could replace the W with B over R.
Okay, so half I omega squared is equal to half I v squared over r squared.
And then we could put in we could replace the inertia, which would cancel out the radius squared, so it would just be 1/2 mass times velocity squared.
When we do 1/2, it would actually be 1/4 because we have 1/2 times 1/2. 1/4 m r squares cancel out. That's just v squared. So then our total kinetic energy is equal to 1/2 plus 1/4 3/4 mv squared. So that's how we get our total kinetic energy as our disk rolls down the slope based on its velocity. So how can we use this knowledge to find the velocity of the disk after it's rolled 2 meters down the slope?
Well, we know that it starts off at rest, so we could find its acceleration.
How would we find the acceleration?
Oh, would it be too complicated to use the kinematic equations?
You could do it, but it's going to be a bit annoying. So you mentioned it starts at rest. So what's its initial kinetic energy?
0.
And what's its initial potential energy?
Its initial potential would be the gravitational potential energy.
Is there any other potential energy?
No.
No, there's not. There's no other potential energy. It's literally just gravitational potential energy. So as the disk rolls down the hill, its gravitational potential energy, what's gravitational potential energy again?
Oh, it's mass times gravity times the height.
Exactly. And how much higher is it? So when I say it rolls 2 meters, I mean if this is the slope, it's rolled 2 meters along the slope. So how much higher up is it initially versus after 2 meters?
Well, the slope's at 30 degrees. This is 2 meters. The 2 times sine of 30.
Mm-hmm. What's the sine of 30?
Sine of 30 is 1/2.
Mm-hmm. So it's just 1
So
meter.
it'd just be 1.
So essentially and if we define our potential energy to be 0 here at this point, because it doesn't matter where we define it, we know our initial total energy is equal to, so this kinetic energy is equal to our total final energy, so E final, which we know is equal to the initial total energy, and we know the initial kinetic energy is 0, which is equal to mgh, which is mgd, the distance we roll, over 2, because that's sine of 30. So then we can just solve for the velocity, right?
Yes.
So it would be 4 over 3, so 4 over 6, 2/3, 2m, actually the m's cancel out, mgd over 3, and then we take the square root. So what's our velocity after the disk has rolled 2 meters? Two times 10 times our distance rolled, 2 meters divided by 3.
0.5? Oh. Got a square.
I take the square root. Let me actually double check that. 4/3 times 10 times 2 times sine of 30. Yep. We get a velocity of about 3.65 meters per second. So then what would be the angular velocity of the disk after 2 meters?
It would be that number times radius, the radius being... Oh, I see my mistake. Okay. So times around 15.
Is it times the radius?
Oh, my bad. Divided by the radius. So it'd be around 1/5. Right?
What's the radius of our disk?
Oh. What's wrong with me? That's 5. Okay.
We have a 5 centimeter radius. We'll keep everything in SI units, so divide by 0.05.
Yep.
We have an angular velocity of about 73. And what's the SI units for angular velocity?
Rads over seconds?
Yep, radians per second. Or radians are unitless, so it's just inverse seconds. So omega is equal to v over r. So then how would we find the angular acceleration of the disk due to the incline?
Angular acceleration.
This is where we could actually start using the kinematic equations.
So we could use the final. Oh wait, we don't have a time. So it would have to be the last of the kinematic equations for rotation.
So this one right here.
Yes.
So plug it in. What's our, well, we know our final angular velocity. What's our initial angular velocity?
Would be 0.
Exactly, 0 is equal to 2 alpha. That's what we want to solve for. What's our total distance rolled in terms of radians?
Total distance. Oh, so we rolled 2 meters. That's
How do we get from the distance rolled to the total amount rotated?
we would find we would use the frequency.
What do you mean by that?
We would find the revolutions.
Yep. How many revolutions are we going to undergo? That's what we're trying to find. We're trying to find this total, this theta minus theta initial, essentially delta theta.
11.6.
How did you get that?
Be the angular velocity divided by the by 2 pi.
But the angular velocity is changing as we roll, right? It's not constant.
Yes.
How can we relate it to the distance rolled, the 2 meters? And also, I should probably do this. He isn't using D to represent these distances. He is using S. S is 2 meters. How do we get theta?
So we would divide S by the radius.
Exactly. It's just our S divided by the radius to get the total amount rotated, the total number of radians rotated. So then, to solve for the angular acceleration, it's just r omega squared over 2s, which if we plug in the values and we calculate it, what do we end up getting?
333.
333. Did you... What values did you use for everything? What's the radius again?
Oh, I keep forgetting to convert it to meters.
Even then, you're still...
It's a lot.
There's still
I
something
used
wrong.
73 for the... Oh, shit, that's the velocity.
73 radians per second is the angular velocity.
I squared that, yeah, and then multiplied it by the 5 centimeters.
So 0.05 meters. Divide it by...
Divided by 2, what was it? 2 meters?
Yep, 2 times 2 meters, so divided by 4. I got about 200 over 3, or about 66.67 radians per second squared. Which should make sense, right?
Yes, makes sense.
So,
That's right.
so how many times would our disk have rotated after 5 total seconds? How do we find how many times the disk has rotated after 5 seconds of rolling down the hill? If we know the angular acceleration now.
Could just you could use the first equation, cancel out the angular acceleration, the initial angular acceleration, because it's 0.
Is the initial angular acceleration 0? Or...
Yes, because it's at rest, right?
Oh, you mean the initial angular velocity is 0?
Oh, yeah. Velocity, my bad.
Yep. So angular velocity is 0, so it's just half alpha t squared. And that would give us the total radians rotated. So theta is equal to half alpha t squared. How do we go from radians rotated to the number of times the disk rotates?
We would just find, so we would just divide it by 2 over pi. I mean 2 pi.
Exactly. Just divide by 2 pi. And we could go ahead and calculate a value. Squared divided by 2 divided by 2 pi. So the disk is going to have rotated about 130, almost 133 times after rolling for 5 seconds. That's a lot of rotating. That thing's spinning real fast.
Yeah.
So what would the angular velocity be after 5 seconds?
Your velocity be could just use the A equals dw over dt. Oh wait, no. Yes. Oh yeah. We could just use the second one because we know the initial would be 0. So it'd just be the angular velocity times the time.
Mm-hmm. And how long would it take? It's 5 seconds. So, yeah, we just multiply it by 5 seconds. Oh god, I closed my calculator. No! So we have our angular acceleration times our 5 seconds. It's rotating at about 333 radians per second after 5 seconds. Do you have any questions about this so far?
No.
No?
I think I understand.
All right.
Yeah.
So if our disk starts 100 meters above the bottom of the incline, so this height here is 100 meters, how long is it going to take the disk to reach the bottom?
Oh, wait, which... So the height straight up is 100, right?
Mm-hmm.
Would we, uh, to start off, would it be good to find the final velocity of the wheel?
Sure. How would we do that?
Um, you would start off with the initial energy equals the final energy, because we can easily find the potential energy of the wheel when it's at the top.
Exactly. So we'll have initially it's mgh plus 0 kinetic energy. At the end, it's all kinetic energy, which is 3/4 mv squared. M's cancel out, and we get our final velocity is 4gh over 3 square root. And what would this final velocity value be? It's going to be moving at about 36.5 meters per second. So now we have this velocity, what do we do next?
Hello?
Hello?
Oh, sorry, I couldn't hear anything for a minute.
Oh. I was saying, so now that we found this velocity we just solve, initial and final energy and solve for a velocity, what do we do now?
Oh, now we could find the final angular velocity.
Mm-hmm. How do we do that?
So we would just divide the velocity by the radius.
Exactly. So we just divide our velocity by our radius, which is 0.05 meters, about 730 radians per second. And then what?
Then we'll plug it into... What is it? Choose how long it'll take. Oh, okay. I guess first we would have to find the acceleration.
And do we know what the acceleration is?
Yes.
Yep. We still know it from before. It was like, what, 66.67?
Yeah, so we could just plug this into the omega equals the initial plus AT.
Exactly. What's the initial?
The initial is 0.
0. And so we just divide our final omega by our angular acceleration. And so it takes us a little less than... So, hold on. T is equal to omega over alpha. And so we get a final time of about 10.95, just under 11 seconds to roll all the way down the slope.
That's pretty fast.
Yeah. Do you have any questions about this? Does that make sense?
Yeah, that makes sense.
All right. So one more thing, not actually going to have us go through and recalculate it again, but how would this all change if instead of a disk rolling down the hill, it were instead a sphere with the same mass and radius?
If a sphere's inertia is 2 over 5 mr squared, so we would just have to redo the part with the kinetic energy.
Exactly.
When we found the velocity.
Mm-hmm. So it's 2/5 mr squared. And then that would, so because the moment of inertia has decreased ever so slightly, then that means that it's going to rotate more. It's going to more easily rotate. So that means it would essentially just slightly change all of our values to where the velocity would end up being slightly more. And therefore the angular velocity and the angular acceleration and everything would be slightly higher. Do you have any questions about any of this?
No, I just think I need to look it over again.
Yeah. Do you have any specific problems you want to go over from your homework or discussion or whatnot?
Not at the moment. I've just been going over them really slowly. Oh, I guess for the discussion.
Yeah, was there any question from the discussion you wanted to go over? Because I do have it pulled up right now. Anything specifically about torque? Because my problem, I mean, we went over what torque was at the beginning, but we didn't actually end up using it too much here.
Oh, I think that my confusion with torque is... I was really confused about question 6, but I think that's just because I was confused about how to calculate torque, and so...
Okay, so question 6. We have a 20 centimeter diameter disc, mass 5 kilograms, that can rotate about the z-axis, pointing on the page. It's subject to 4 forces. The disc is initially at rest, and the moment of inertia of the disc about its center is half mr squared. So first thing we want to know is, what are the x and y components of the net torque about the z-axis? So first of all, we want to find the total net torque, right?
Yes.
There's 4 forces, so there's going to be 4 torques. One of them is 0. Which one of these forces is not going to contribute to the torque?
So if it's... it would be the 20 that's outside of the circle.
Exactly, and why is that? Why does it not contribute torque?
Because it doesn't have any... it has to have some sort of force acting upon it in a perpendicular sense, but in this case it doesn't.
So what you're saying is because the force is parallel to the displacement vector from the axis of rotation, the torque is 0?
Yes.
Yep, exactly. So now, how do we find the torque from each of the other forces?
So the only one that's so for the 30 that's kind of slanted, we would have to multiply that by sine of 45
Mm-hmm.
because it's not perpendicular to the torque.
Yep.
Before the other ones, I think we should just be able to multiply the dis like the distance from the origin to the force times the force.
Yep. So, what is the total x and y component of the net torque about the z-axis? What direction are each of these torques acting in?
Are all of them acting on the z-axis? Or are they?
What direction is the top force? What direction is the torque acting from the top force?
Oh, it's directing clockwise?
Clockwise, which means the torque is in what direction?
Inwards?
Exactly, into the page. What about the bottom left 20 Newton force?
The 20 force is acting counterclockwise. So it would be out of the page.
Mm-hmm. Out of the page. So both the top 30 and the bottom left 20 Newton force both have only z-axis components of the torque. There's no x and y components. And now the diagonal 30 Newton force, so what direction is it wanting to rotate?
In, like across the page? I'm not,
What do you mean by that?
I'm not sure about that one. Well, because it's acting in that direction, wouldn't it just pull? It'd be pulling on the disc instead of rotating it.
Well, it's still going to rotate the disc. See, let's break this force. Let's break this force into an x and y component. What direction is the torque going to be from the x component of the force?
Gonna be towards clockwise.
Is it clockwise? Hold up, let me screenshot this and so I can draw with it on Paint. So I think I want to visualize this. I think this will help you. Oh. Oh crap, what the hell's happening? Okay, boom, boom. So zoom in. So we're gonna go ahead and break this diagonal force into an x component and a y component. What is the x component? What is the x component going to do torque wise?
Oh, the x component's gonna pull it downwards, so counterclockwise.
Is it?
But it's pulling out to the left. It should be the opposite of the other one. I guess.
It's anti-parallel to the displacement vector, right?
Oh.
So is there any torque from the x component of the force?
No.
No. What direction is the torque due to the y component?
That one's towards clockwise.
Is it?
Or is it also 0? In terms of
Well, we go out to the right and then we're pulling upward.
Oh, so it would be going counterclockwise.
Counterclockwise, so what direction is that torque in?
Out of the page.
Out of the page. Are there any components of torque in the x and y direction?
Um, would it just be in the z direction?
Exactly. It's only in the z direction. There's only z components of the net torque. So what are the x and y components of the net torque about the z-axis? Is 0. What's the z component? Well, now we have to actually calculate the total net torque. And you mentioned that for the 5 centimeter, for the 20 Newton force here down on the left, how do we calculate the torque?
Just be 20 times the 5 centimeters.
Exactly.
So 0.
So 20 times 0.05. So 1, and then the, what would be the units for torque? I'm blanking. It'd be Newton meters. Yeah, Newton meters. So 1 Newton meter. And we'll say that's positive because the torque is in the positive z direction. So counterclockwise is positive. The 30 Newton force here, what direction is it acting in?
Clockwise, so it'd be negative.
Negative, and this radius here is it 10 centimeters?
Oh yeah, so it's
Does it
20 centimeter diameter.
Yeah, so 10 centimeters. So minus 0.1 times 30. So we total torque of -2 from those two. And then the third one, the diagonal force.
Oh, so that'll be 30 times sine of 45 times the radius.
Times 0.05 times the sine of 45. And is it positive or negative?
That one's positive.
Yep. So we get a total net torque of negative 0.939 Newton meters. So essentially a clockwise rotation, 0.939 Newton meters. So how do we go from this torque to the magnitude and direction of the angular acceleration around the disk?
Well, we can find the inertia from what's given to us. And torque is equal to the inertia times the angular acceleration. So we just divide the torque that we found.
Exactly. We just divide our torque by the moment of inertia, which is half mr squared, 0.5 times the mass, which was 5 kilograms, times the radius, which is 10 centimeters, 0.1 squared. We get a total angular acceleration of negative 37.6 radians per second squared. And what direction is it in?
Clockwise?
Exactly. Clockwise. It's the same direction as the torque. So then, what would be the rotational kinetic energy of the disk after 5 seconds?
So we would use the equation W, it's omega, right? Omega equals the initial plus the acceleration times the time, so we would just cancel out W because it begins at rest.
Mm-hmm.
And we would multiply our acceleration times our time.
Yep. Omega is equal to alpha t. It's 5, so we get an angular velocity of about 188 radians per second clockwise. And then how do we go from that to the rotational kinetic energy?
Oh, then we just multiply 1/2 of our inertia times our velocity squared.
Exactly. Times 0.5. Well, I mean, it's this squared. Times 1/2 times the moment of inertia, which the moment of inertia itself is 1/2 times the mass times radius squared. So we get about 441 joules of rotational kinetic energy. And then if the top force, the 30 Newton force, was removed at that time, how long would it take the disk to come to rest? How would we do this?
We could find our net torque without the 30 newtons.
Mm-hmm.
And then find
So we get our total net torque.
and so we could then find our new acceleration because we still know what the inertia is from our previous.
Yep,
And then we
exactly.
could use that acceleration in the same equation we used before, except the previous velocity we found would be our initial and our final would be 0.
Yep, exactly. So this is our angular acceleration, and then we have so which equation do we end up using? The second one, right?
That one?
Yep. And so our final, so we have our acceleration, and then we have our initial, plus this times time is equal to 0. And so it's going to take us about 2.28 seconds to come to rest. Do you have any other questions?
No, I think that's it for now.
All right. Well, I mean, once again, it's mostly just going through and practicing, and it seems like you're pretty comfortable with this material, honestly. Like, you're definitely way further ahead of most of the people in this class, I'd guess, in terms of actually being comfortable with this rotational kinematic stuff and understanding it.
I feel like I still need a lot of practice.
Yeah. You'll always feel like that, where it's always going to feel sort of uncomfortable, but like as long as you just take everything step by step and break it down, take a look, worship the equation sheet and break everything down into stuff you understand. So for every question, write down what you're given, what you want to know, and how, and any equations related to them, and try to connect the dots. So hopefully this helped out, and good luck studying for the quiz tomorrow, and same time on Sunday going over tomorrow's material.
Thank you.
Good luck studying. See you around, Alicia.
Bye.
Bye.